the December virtual meeting of the Central Florida Astronomical Society, meeting virtually since, I believe, April was our first virtual meeting due to the pandemic. And we can always blame the college if it's just easier to blame the college for closing the planetarium. Then we don't have to have any awkward explanations, although I don't think that really is required. So for tonight's meeting, which is obviously not going to be our holiday party, I'm very, very sad that we had to skip that this year. We've got some nice things coming up after our announcements and events. We have a talk on gravitational waves and LISA. We'll have a rundown of member photos and sketches from Derek. Also, John Pinto, who I did not know is a fellow astronomy computer enthusiast, is going to talk about calculating winter solstice. Also, Derek's going to have a special edition of Tonight's Sky, because if you haven't seen it, Jupiter and Saturn are doing a thing this month, and you're not going to want to miss it when they do their thing this month. And Derek's going to talk all about it in a little bit. I'm going to take a break from all that deep sky stuff to spend just a minute on the moon. And then Sharife is going to talk about her Artemis project, her art project. I've seen some of it. It's quite fantastic. Actually, you are talking about the art project, not about going to the moon. Which one are you talking about?
Artemis 1 and 2.
Okay. Well, I'm going to stop embarrassing myself. Then we're going to have a book review. Cosmos, no, not that Cosmos, a different one from our astronomy historian, Taryn Hill. So it occurred to me, or occurred to us, occurred to somebody on the board who reminded me, I don't remember what the exact chain of events was, but when we used to meet in person, we used to say, hey, do we get any visitors? And well, we don't have any visitors because in order to prevent unfortunate accidents, only members can join the Zoom feed live. But we also used to do, hey, do we have any new members? So I'm going to say, hey, are there any new members that want to introduce themselves to the club? Speak up, raise your hand. Derek or Frank can, I think everybody has screen sharing abilities, don't they? Actually, I think you all do. So is there anybody that wants to speak up and introduce yourself? It's going to be real awkward if I made all of this and there's not even a single new person who wants to embarrass them. I mean, introduce themselves so that we can get to know you. No new people. You're looking for that button. All right. If you do, just go ahead and interrupt later. It'll be just fine. Okay. So further reminders this month. Remember, the official CFAS communication group is through Groups.io. We're trying to get that going. We do have a lot of people still on Facebook, which is fine. We're not going to shut down the Facebook. But we want to remind you that the Groups.io is a nice, perhaps safer place to exchange notes about what's going on in the astronomy community. Also, our new-ish, I'm going to have to stop saying new soon, our publicity chair, Sharife, is also looking for astrophotos to use in our social media efforts. I know some people sent her some. Keep sending her some more. She's nodding right now, so she definitely would like some more. And there's her email on the screen. And if you miss it here, you don't write it down fast enough, you can always hit print screen, but you can also always come back and get this off of the YouTube video, which we post later. Also, remember those Royal Astronomical Society of Canada observing handbooks and calendars. They are in. So Kent, our treasurer, got a big box of them. I was going to slug it out at a Starbucks or something, but Kent said, no, just send everybody to my house. So thank you, Ken. You can email Ken for a good time to show up. I'm quite sure after midnight is not acceptable. Also, he does have a job, so let him know that you're coming ahead of time, and you can pay with a check or money order, or I believe you can also do it over PayPal as well. And actually, I need to make arrangements to go and pick up my book as well. So things are slow this month. We have no holiday party, and of course, events are somewhat blunted by our inability to meet together. The planetarium is doing a big show with Jupiter and Saturn. I think it's amazing that Derek arranged for these two planets to get so close together just for this event, but I'm not going to steal his thunder. He's going to talk more about that later. Also, I wanted to tell you that next month's meeting, we're going to do another pre-meeting sort of Cosmic Clubhouse sort of thing. So we did one a couple months ago about, so you're looking for a telescope. We'll give you some ideas. This next one is, so you got a telescope for Christmas, now what? And that meeting that we are going to open up to the public as well. And that's actually it. That's my last slide. So I'm going to let Tricia introduce our main program, and then we'll get into our mini programs after that. Let me stop sharing. Take it away, Tricia. I can hear you.
Okay. Welcome, everybody. So tonight we are very excited to welcome Dr. Shane Larson to CFAS. Now, a little bit about Shane before we have him start here. Shane is a Research Associate Professor of Physics at Northwestern University, where he is also an Associate Director, or I believe now maybe Director, I'm going to check with Shane, of Sierra, the Center for Interdisciplinary Exploration and Research in Astrophysics. He works in the field of gravitational wave and astrophysics, specializing in studies of compact stars, binaries, and the galaxy. Shane grew up in Eastern Oregon and was a graduate at Oregon State University, where he received his BS in physics in '91 and his PhD in theoretical physics in '99 from Montana State University. He's an award-winning teacher and a fellow of the American Physical Society. He currently lives in the Chicago suburbs with his wife, daughter, and cat. He contributes regularly to a public science blog, writescience.wordpress.com, and he also has a website, sciencejedi.com, which I'm going to link here any second in the chat. So if you're all welcome, Dr. Shane Larson to CFAS. Clap, clap, clap.
Okay, thanks everyone. So it's great to be here. Thanks to Tricia and Derek for the invitation. Some of you I may have met before or seen before. I do travel around to star parties. Of course, we haven't been doing star parties this past year, but we will again in the future, almost certainly. And so if we do run across paths, please do say hello. I'm both a professional and an amateur astronomer, and so one of the things I do enjoy quite a bit is going out and talking to my fellow amateur astronomers about what me and my fellow professional astronomers do. So I will apologize ahead of time because as I give my talk, I will often use the pronoun we or us, and sometimes I mean we or us the professionals, and sometimes I mean we and us the amateurs. So I'll leave it up to you to figure out which group I'm talking about. I apologize for that. I just switch seamlessly back and forth in my head about that. So I'm going to talk about gravitational waves tonight. I'll talk for kind of 35 or 40 minutes, and then I'll take questions for as long as the hosts let me afterwards. But I'm certainly happy to answer questions if they occur to you sometime later, long after the meeting is over. You can certainly find me on the web at the Northwestern website and send me email, and you can certainly contact me over my social media, which will be on my first slide. Those of you who have heard me talk about gravitational waves before, I focused on LIGO a lot because LIGO has been in the news very prominently over the last 5 years because of the first discovery and many interesting subsequent discoveries. But tonight, I'm going to talk about gravitational waves in general, for those of you who don't know much about gravitational waves, but I'm going to focus mostly on LISA, which is a future observatory that I've worked on for my whole career, and now I'm very deeply involved in. So here in the background behind me is an artist's rendition of the LISA spacecraft. It is roughly life-size. The full spacecraft is about 2 meters from one side of the top solar panel to the other. And what you and I care about as amateur astronomers is where you see the lasers coming out here and here are actually telescopes, not unlike the telescopes you and I are used to. They are going to be somewhere in the 30 to 20 centimeter diameter size, although at that aperture, you and I are probably used to much slower telescopes than the ones here. I think the ones on LISA are going to be something like f1.1 or f1.5. So they're very fast, but they are telescopes. And what they're responsible for are for sending out and receiving these laser beams that you see flying out of the spacecraft. And we'll talk a little bit about that when we get deeper into the talk. Okay, so let me go ahead and share some slides. Okay, So we're going to talk about gravitational waves. There's the link to my blog, which you heard Trisha mention. It is a blog aimed at the public. As I like to tell people, it's so my mom knows what I do. I'm an astrophysicist, but my mom's a forester. So I try and kind of talk about astronomy and stuff there in context that she can certainly follow. So hopefully you'll find some useful stuff there. I talk a lot about gravitational waves, or I have over the last several years with the discovery. So there's lots of stuff there, but I talk about various things in astronomy as well. There's my links to social media, which you can certainly find me at, okay? So almost everything that we know about astronomy, that you read in a textbook, that you read in Sky and Telescope, that you read in newspaper articles, that you were taught when you sit in astronomy classes, are things that we have gleaned, almost all of it, through the use of telescopes. And for the entire 400 years since the telescope has been invented, that has been true for both professionals as well as amateurs like us. And so these are my two telescopes that you'll see me out at star parties with. That's Equinox on the left and Mariner on the right. But the design and operation of telescopes has largely not changed since the invention of designs that you and I are very familiar with. What has changed is the technology around them, the advent of attaching cameras and instruments like spectrographs, the engineering of the telescopes themselves so that we could build ever larger telescopes. But the fundamental technology itself, the telescope, is designed to gather light in all its myriad forms. And from that simple measurement, we have deduced almost everything you've ever been taught about astronomy. But today, we live at the cusp of a brand new branch of astronomy that we call gravitational wave astronomy. And just like electromagnetic telescopes, there is a network of these observatories springing up around the world. This is, it's actually outdated now that I'm staring at it, but this is the world network of gravitational wave detectors. The outdatedness has to do with the yellow dot over there on the far right. That is Kagra in Japan. They are now operational since just about the start of the pandemic is when they came online. But there's this globe-girdling network of efforts to measure the universe, not with light, not with the traditional things that we're used to, but with gravity itself. And we'll talk about that a little bit more as we get in. The ones you're familiar with, perhaps, are the LIGO observatories here in the United States. They are two more or less identical facilities. One's located in Hanford, Washington, and one in Livingston, Louisiana. We have for a long time been working in concert with our partners called Virgo, which is right outside of Pisa. It's a little bit smaller than LIGO, but roughly identical in configuration, slightly different technology in the guts. There's a smaller one in Europe called Geo 600, where we do a lot of our technology demonstration. There is going to be a copy of LIGO built in India. That'll be online in the next 5-ish years or so. And Kagra is similar in design to LIGO and Virgo. They're a bit more advanced in their technology, and they are built actually underground. So on the surface of the Earth, there will soon be a network of 5 or 6 of these gravitational wave observatories that we use to observe the cosmos. Right now, 3 and now 4 of them, now that Kagra's online, are used. You'll see the pink dots. Those are a specialized form of radio astronomy using radio telescopes. Sorry, a specialized form of gravitational wave astronomy using radio telescopes called pulsar timing. We'll mention that in the end there. But what I'm going to focus mostly on is LISA, which you see up there in the upper right. That is a space-based observatory that will be built and flown in about 10 years or so. Oh, sorry, and then there's also down at the South Pole, they are observations of the cosmic microwave background, which is another detection method, which I'll mention briefly later. So how do we fit this kind of new technology and this new approach into the way that we think about and the way we do astronomy? And to enter that conversation, I like to start with something I call the spectrum parable. Now, some of you may know this story. This is a very famous story in astronomy, but it has to do with William Herschel. And in the 1800s, early 1800s, we were just beginning to get comfortable with the idea that physics and astronomy were linked. And so in particular, astronomers were trying to understand the properties of light because they knew that everything we learn about the universe we can discover from light. So this is the time when spectroscopy was being developed, where our understanding of what spectral lines in spectra were slowly coming to bear. That would happen maybe 15 years after this moment with Fraunhofer and the discovery of lines in the sun. But Herschel was trying to understand what's the difference between the different colors of light that you can produce when you take the light from an object like the sun and pass it through a prism. So you see here, he's passed the sunlight through the prism and it makes the traditional rainbow. And what he had done is he was putting thermometers in the different bands of color in the rainbow to try and understand if blue light was different than yellow light, was different than red light. And as the story goes, he accidentally left a thermometer right outside the red part of the spectrum, as you can see there in the artist's rendition on the left. And he noticed that the temperature in that thermometer was climbing, despite the fact that he thought there was no light on the thermometer. So this was the discovery of what today you and I know is infrared radiation. It's a form of light that absolutely exists. It has properties, wavelength, frequencies, amplitudes, all those things you can measure about light that the normal colors of light do, but it's completely invisible to our eyes. And that discovery set off a long chain of discoveries, which culminated in the mapping out of what we call the electromagnetic spectrum. Okay, so the traditional part of the spectrum that you and I observe with our eyes is appropriately called the visible spectrum. It's what's visible to human eyes through the evolution of human physiology. But what Herschel set off was the discovery that the spectrum extends far beyond just this very narrow range of the rainbow that you and I are used to. Now, the amount of space that the rainbow takes up is much, much smaller than I've represented it here, but I've spread the diagram out a little bit so you can read. And so what I'm showing here are the, in the middle row, are objects whose physical size, the dimension, if you could measure it with a ruler, is roughly equivalent to the physical size of the property of the light that we call the wavelength that physicists and astronomers use to characterize what kind of light are we actually looking at. So if you look at the diagram there at the top, that is a heuristic diagram that shows over on the left-hand side of the spectrum, well above the blue light that your eye can see, are what we call short wavelengths. So the light that we characterize gets shorter and shorter in terms of those wavefronts that represent its actual physical property. Okay, and there's a one-to-one mapping between color and wavelength. And if you go to the right, down below the red, you go to ever longer wavelengths. And so for those of you who know about the electromagnetic spectrum, you remember it from your physics class or chemistry class, or you study this yourself, you'll see there right underneath the red wavelength that I've drawn, the traditional names for the different kinds of light. And so at the very shortest wavelengths, we have gamma rays, and then X-rays and ultraviolet light. Then we have the visible spectrum, which you and I can see, and then the infrared light, microwaves, and radio light. All of these things, even though you hear about microwaves or radio waves, or you hear about gamma rays or X-rays, they all are just light. The language is recording the fact that historically we had discovered high energy phenomena that you and I now call gamma rays or X-rays, but we didn't necessarily always know it was light. And so those kind of names that we used when we were first discovering the phenomena carried on. Okay, but these are the traditional names that you'll learn. There are actual numbers that go with all of these if you want to do calculations yourself. But these were slowly discovered over the course of 200 years or so. Now, the problem with all of these is that we don't necessarily have the ability to measure them. Herschel, quite by accident, discovered infrared astronomy with the thermometer. But as you know probably quite well today, we have telescopes that can take pictures in infrared light exactly the same way you and I can take a picture with our telescope in our backyard. It just uses a different kind of detector technology to sense the infrared light. Okay, and so since the discovery of all of these wavelengths, the technology to record and image with each one of these different kinds of light has been slowly developed, and it took about 200 years for all of them. But what we as astronomers have discovered, quite to our surprise, is that every single one of these different kinds of light is useful for studying the cosmos. So the kind of classic example that we show to illustrate that is we take an object that we're very familiar with in the visible light, and we show you what it looks like in all the different kinds of light that there are. So this is the famous Antennae galaxy, which many of you may have seen. You can see it in the constellation Corvus. It is two colliding galaxies. The optical image from Hubble is right there in the bottom. You can see the two bright bulges of the main bodies of the galaxy slowly coming together, and they leave behind them what the galaxies are named for, these long, as we call them, tidal tails, these streams of stars and gas and dust that are being gravitationally stripped off of the two galaxies as they collide. If you look at the antennae in optical, it looks much like the Hubble image there. And I'm sure most of you have amateur astrophotography friends who are very good at creating images like this. But if you look at it with telescopes designed to see in light that your eye can't see, you get all of the images that surround the optical image there at the bottom. And what's remarkable about all of these is that they all kind of look the same. That is, you can see the kind of core bulges of the two galaxies, but every one of them looks different in subtle and interesting ways. They are bright in some places and dim in other places. Their shapes are irregular or have holes carved out of them or what have you, all kinds of differences. And if you spend hours staring at this image, you can come up with all kinds of great differences between them. And that's a good exercise to give to your kids while they're at home, being bored during the pandemic. Give them these pictures and, do the whole, these pictures aren't the same, name all the differences. It'll take them hours to find all the differences. So what's the point for astronomers though? The point for astronomers is that every one of these different kinds of light is illuminating different physical processes that are driving the evolution of the galaxy. So if you go all the way over to radio and infrared light, those kinds of images are dominated by the gas and dust in the galaxy. You get emission from the thermal heating of dust and through the plasma interactions of the gases. If you go all the way over to the high energy side, to the X-rays and the gamma rays, then all of those emissions are dominated by high energy astrophysical processes, typically accretion onto very compact objects like black holes. If you go into the middle there in the optical, you see those kind of very blue regions, especially the ones that stream out along the tidal tails. That's places where the gas has been churned up, and when young stars light up, forming out of all the disturbed gas, they emit very blue light. So astronomers take images like this and they disentangle the story of a pair of galaxies that's millions of light years away that no human will ever be able to visit. We disentangle the story of what's going on by adding to the table of knowledge that we have about this object all the different ways of looking at it in the different kinds of light. And that approach to astronomy is really the most important thing about what gravitational wave astronomy is all about. Gravitational wave astronomy is a completely new and different way of looking at the cosmos. It's a way of looking at the cosmos that we as humans don't have any preconceived sensory ability to understand. All of us are used to seeing the universe. Most of us are used to seeing the universe with our eyes and sensing with our normal senses, but none of us has a gravitational wave detector built into our elbow. Gravitational waves are a physical phenomena that we predicted mathematically. We went out and discovered, wow, this does exist, and so we are now using it for the first time to measure the cosmos in ways that we haven't ever been able to before. And coupling those kinds of abilities with images like this give us really great capabilities in astronomy. So let's talk about gravitational waves and what they are, and then I'll tell you a little bit about LISA. So you've probably seen many animations of gravitational waves. The kind of traditional one that you see looks like ripples on a pond, but this is the one that I actually like to show because I think it more accurately represents how these kinds of waves are useful for astronomy. So what are you staring at? What you're staring at right here is two black holes. And they're in orbit around each other. They're in a very close orbit around each other. They're going around each other at half the speed of light. These are objects that are about the size of the city of Orlando. They're going around each other and slowly spiraling together and merging. And one of the things that Einstein taught us was that no information in the universe can travel faster than the speed of light. And in particular, if two black holes are moving around, then the gravity from those black holes is constantly changing because sometimes they're farther away from you, sometimes they're closer to you. As they move around in their orbits, that information about how strong the gravity is where you're standing has to change, but it can't get to you at a speed faster than the speed of light. And that's really what gravitational waves are all about. They're all about the idea that changing information about the gravitational structure of astrophysical objects like binary black holes has to travel through the universe at finite speed. So what this movie is showing then is the wave fronts of the gravitational waves. Just like that red line in the electromagnetic spectrum I showed you a few minutes ago, the bright lines in this movie are like the tops of those wavy peaks I showed you in the electromagnetic spectrum. And what you see is as the black holes move around, those wave fronts, as we call them, those peaks in the waves, travel outward from the source. You should notice that they travel outward in every direction. And this is why this is a better movie than the normal traditional ripples on the pond movie that you see. Every direction, no matter where you are in the universe, if you have the technology, you can observe these gravitational waves. It's just like a star. When a star shines, it sends its light out in every direction. And it doesn't matter if you're sitting in the orbital plane of the Earth or if you're sitting well above the North Pole of the sun, you still get light from the sun. And the same thing's true of gravitational waves. They travel outward from these sources of gravitational waves in every single direction, which is why this is useful for astronomy. You'll notice as the black holes get closer together, the intensity of the colors gets brighter. That's because the gravitational waves are getting brighter. And you'll notice when they merge and become a single black hole, the gravitational waves fade away. And that is because the gravity is no longer changing because the black holes themselves are not moving anymore. Okay? So that's the fundamental underlying thing that we're looking for. Binaries are the easiest way to visualize this. There are, of course, many other ways of generating gravitational waves in the universe, but all of them involve the motion of masses, and that's what we're looking for when we measure gravitational waves. Now, just like electromagnetism or a light, gravitational waves cover an entire spectrum. And so here I've shown you the complete span of the gravitational wave spectrum. I've cleverly color-coded it with color from purple to red that follows the normal spectral color that you and I are used to. So just like in the electromagnetic spectrum, the red side are longer wavelengths of gravitational waves, or as we tend to like to think about in terms of frequency, lower frequencies, more bass notey sounds. Okay, and as you go to the purple end, those are shorter wavelengths or higher frequencies. Okay, over the frequency bar there, you'll see something labeled periods. And so that's roughly the time scale that astrophysical objects have to change on in order to generate gravitational waves at each part of this spectrum. Now, the four bands there correspond to the different bands, the different ways that we've developed technology capable of detecting gravitational waves. And this is one of the great things about gravitational waves compared to the electromagnetic observations, observing the universe with different kinds of light, is it took almost 150 years to figure out, if I start with a telescope like Galileo built, how do I now build a telescope that can detect gamma rays? Right? The technology took almost 2 centuries to mature to cover the entire electromagnetic spectrum. But in the gravitational wave spectrum, we are simultaneously building technologies that are capable of detecting gravitational waves across almost the entire band where we expect things to happen. So over on the very far left, you see the cosmic microwave background experiments. Those are basically looking for the influence of gravitational waves in the spotted structure of the cosmic microwave background. You see our pulsar timing friends there in what we call the nanohertz band, the green band there in the middle. They basically look at the signals from distant radio pulsars, and gravitational waves change how those arrive at Earth. On the far right, you see the LIGO detectors, which are the famous ones that have been in the news. That particular one is the one in Livingston, Louisiana. And what I'm mostly going to talk about to you right here is the one in the middle, which is LISA, okay? Now, the reason we're trying to span the spectrum as we are is that when we look at the spectrum, there are sources, expected sources of gravitational waves in every part of the gravitational wave spectrum. And this is what astronomers are really, really excited about, is no matter where we look in the gravitational wave spectrum, we expect to detect something that you and I know about, that we've read about in astronomy books and Sky and Telescope or whatever, okay? But we'll be able to learn new things about them because we're going to study them not with light, but with gravity instead. And up here, you see why you hear so much about LIGO and very soon about LISA, is this is where lots of the action is going on. There's lots of different kinds of things that we can observe in the higher frequency parts of the gravitational wave spectrum. Okay, so let me tell you a little bit about LISA. I'll tell you some things about the things that we're going to see. So LISA is going to be an observatory, not unlike the observatories we're building on the ground, but at the same time completely different. It's 3 individual spacecraft. They're identical, okay? And so these are like the spacecraft in the background that you see here behind me. This is a different artist rendition that has this kind of octagonal solar shield on the top. But what they do is they shine lasers from one spacecraft to the other. So if you were to cover up this third arm here and just look at 2 arms, 2 laser arms, and 2 spacecraft, it looks kind of like the LIGO detectors, which are a big L. LISA is a part of a triangle, so it looks like a bent L. But it kind of functions the same way. Okay, and so what we're doing is we're timing how long it takes a laser beam to fly from one spacecraft all the way to the other spacecraft. And then we shoot another laser back and time how long it takes. And what gravitational waves do is they stretch the distance between the spacecraft. So sometimes the laser light arrives early and sometimes it arrives late. And we use that arrival time to measure the gravitational waves. The distance between the spacecraft is 2.5 million kilometers. So it takes about 8.5 seconds or so for the light to travel from one spacecraft to the other. 2.5 million kilometers is quite large, so this will be in space. It will be behind the Earth, and so this is a movie showing a full year orbit of the LISA spacecraft. You'll see they maintain the triangular configuration. That's a very special set of orbits that we've discovered. You can derive them yourself. There is only one set of orbits for which this triangular configuration that you see here works. It's a good exercise for undergraduate physics students to work it out, but it will follow the Earth in this triangular configuration, doing this cartwheel that you see it doing, slowly rotating over the course of a year, and it will maintain its shape for about 10 years or so before perturbations stretching from the moon and planets and other things in the solar system slowly cause the spacecraft to drift apart. Okay? So why do we even think about building LISA when we already have built something like LIGO? Well, the answer is right there in the electromagnetic spectrum, and in the parable I told you about the electromagnetic spectrum is that you learn different things by looking at the universe in different colors of light, and in this case, to use the metaphorical analogy, in different colors of gravitational waves, or to say it more precisely, in different frequencies of gravitational waves. So for LIGO, they observe in the very high frequency end of the spectrum. So what they typically observe, and if you've been following the news, you've heard about, are what we call small, fast systems. So these are neutron stars going around each other and merging. These are stellar mass black holes going around each other and merging. Their orbital periods are typically fractions of a second, okay? And they merge, they emit gravitational waves. They're transient, that they merge when they emit gravitational waves, and then they turn off, and then they're gone, okay? There are other sources that LIGO can detect if they happen to occur. Probably the most notable one is shown there on the right. A supernova explosion in the Milky Way should emit gravitational waves that may be detectable by LIGO. Okay, so small fast systems are what we see in the high frequency gravitational wave part of the spectrum, and we use an instrument like LIGO to do that. LISA, by contrast, sees what we call big slow systems. So if we think still in the context of binaries, we're talking about things that have orbital periods not that are fractions of a second, but orbital periods that are much, much, much longer, like 10 seconds, or like a day. Okay, now if you study, say, orbital periods in the solar system, those still sound like extremely fast orbital periods, right? Mercury's orbit around the sun is 88 days. Okay, but the sources that we talk about seeing have these slow by gravitational wave standards orbital periods, 10 seconds to a day or so. And so that includes things like you see there on the left. Those are white dwarf binaries. The Milky Way's stellar graveyard is full of about 10 million of those white dwarf binaries. We'll talk about them quite a bit here at the end. In the middle there, you see two supermassive black holes. So the antennae galaxy, which I showed you at the beginning, are galaxies that are merging. And one of the things that we've discovered in the last 10 years or so is that most big galaxies carry a big black hole at the center. So when the galaxies merge and form one single new big giant galaxy, those black holes sink to the center, and those black holes eventually find each other and they will become bigger black holes. And when they do, they will emit gravitational waves detectable by LISA. Those of you who are paying attention to the Nobel Prizes this year know that we were awarded Nobel Prize for big black holes at the centers of galaxies. Roger Penrose received the Nobel Prize for theory work on black holes. But on the observational side, Andrea Ghez at UCLA and Reinhard Genzel at European Southern Observatory for their observations of the black hole at the center of our galaxy, Sagittarius A star. What they've been observing, and you'll see there, that's a still from the UCLA's movie, they see stars orbiting that big black hole. Now, those stars are pretty far from the black hole, but over time, they will get closer and closer to the black hole, and eventually will fall into the black hole. And when they get to that phase, this kind of source, a small compact object orbiting the black hole, will emit gravitational waves that LISA can detect. Okay, so these are a famous source called Emery's if you listen in to our professional conversations and hear us talking about those things. So let me tell you a little bit about some of these sources and why they're interesting. So the supermassive black holes are ones that most professional astronomers are probably the most excited about. And there's a lot of reasons for that, not the least of which is there's a lot of big black holes in the universe, in the center of bulgy galaxies. But we also know that galaxies collide quite often, and this is just a selection from Hubble of colliding galaxies that they have imaged. There are many more, and some of you may have seen some in your own observations with your telescopes. And so that means this idea that big black holes find each other on occasion and merge is something that happens often by astronomical standards. Now, the reason that's important is one of the mysteries that we have is we don't know, at least with confidence, how big black holes grow at the centers of galaxies. They obviously grow when two of them get together and merge, but the real question is, do they grow that way primarily by colliding with other black holes of the same size? Another option is they grow by absorbing stars. Another option is they grow by accretion of gas. Okay, but this is a huge mystery. We don't actually know the answer. And in fact, it's an even huger mystery when you talk about cosmologically distant black holes, because the most distant quasars are enormous black holes, and we don't have any idea how to grow them between the time of the Big Bang and the time we see the quasars, where we see them in the universe now. So the idea then is, because LISA will be sensitive to these big black hole mergers basically all the way to the edge of the visible universe, that observations of these black hole mergers will help illuminate some of that story about how black holes grow over time. Now, I want to do a demonstration that I often do for people when I do this talk. One of the problems we have in gravitational waves is that we're not used to talking about gravitational waves. We don't have language for it the way we do for the rest of astronomy. Telescopes are really bionic eyeballs, and so it's very natural with telescopes to use the language of vision to talk about what we're doing. We see things. We take pictures of things. And when we make some great discovery, like I discover a colliding galaxy, like the ones that you show here, I send it off to the editor of the Chicago Tribune, and they publish it, and they're very happy. Okay, and most of us have grown up, either we grew up in the age of Hubble or we grew up only knowing the universe through the eyes of Hubble. This is the way people are used to see the universe, with these gorgeous pictures from our giant observatories or from our observatories in space. But when I show people things about gravitational waves, all I have are wiggles that look like those red wiggles I showed you back early on in the electromagnetic spectrum picture. And of course, if I send a graph to the Chicago Tribune editor, the first thing he does is check to make sure I didn't send him my kids' homework from science class. But then he says, go away, kids, you bother me, because they want pictures like these to talk to the world about astronomy. So what's a gravitational wave astronomer to do in order to help people understand viscerally that there's really awesome astrophysical information in gravitational waves, in the same way that you can look at a collection of pictures like this and viscerally understand that these galaxies are somehow tearing each other apart? Well, one of the ways we do that is we take our representations of the data and we turn them into other representations of the data. What me and my colleagues do every day is we show each other graphs. And those of you who've been through science classes, right, you can stare at graphs some, but they're just not as fun to stare at every day. But what we can do is we can take graphs and we can put them on like your phone, okay? And when your phone sees the data representation of a graph, it just looks like a bunch of wiggles, and it knows what to do with wiggles. Right now, your phone has a bunch of wiggles on it that more or less could be represented as a graph, but if it pushes it out through the headphone jack, then you get Katy Perry or Led Zeppelin or Glenn Miller Band or whatever it is you listen to your headphones when you're listening to music on your phone, okay? But if I steal your phone and I replace some of those wiggles on your phone with wiggles that represent my gravitational waves, when you push it out through the headphone jack, you won't hear Katy Perry, you'll hear a representation of the gravitational waves turned into sound. So I'm going to do that for you. I'm going to play, I have 3 total, but I'm going to play 2 gravitational wave sounds for you right now. This isn't what we detect. It's a representation of what we detect. We don't detect sound, we detect the wiggles, and I've just turned those wiggles into sound so you can experience them. And my point in this demonstration is that you, most of you I assume, have no training as gravitational wave astronomers. But I'm going to play 2 different gravitational wave signals for you, and you can absolutely tell the astrophysical difference between them. And that's because your ear is a highly trained astronomical detector, because you spent your whole life learning how to parse sounds and tell the differences between them. And you know the difference between me talking and Trisha talking. You know the difference between me saying astronomy and grilled cheese sandwich, because your ear is used to telling the difference. And in a very similar way, you can tell the difference between these 2 sounds. So I'm going to play 2 gravitational wave signals for you. They are absolutely the identical source. They're a 10 solar mass black hole falling into a 10,000 solar mass black hole. Okay, so these are kind of canonical LISA-style sources. The difference between the 2 sounds is the first one are circular orbits slowly getting smaller and smaller circular orbits until the black holes merge. And the second sound are elliptical or oval-shaped orbits slowly getting smaller and smaller and smaller until the black holes merge. Okay, and you can absolutely hear the difference in those. So I'm going to play these. Derek and I did a test at the beginning, so it should certainly come through, and you should be able to hear it. So let's do the first one. This is the circular orbits. Okay? So that is the famous chirp, as we call it. As the orbit shrinks, it goes from being very long time scales, which is low frequencies to your ears. But as it gets smaller and smaller and smaller, the orbit's faster and faster and faster. So the pitch of the sound goes up. It walks up the keyboard to higher notes. And then it gets louder because the gravitational interaction between the black holes is getting stronger. Okay, and that makes that nice chirp sound that you hear at the end. Okay, so here's the same system. The only thing I've done is I've made the orbital shape different. These are oval shaped instead of circles. Sounds like your car, right? Okay, so those two are the same system. The only difference is the orbits. The reason the second one sounds weird is because the oval-shaped orbit, sometimes the black holes are close together and sometimes they're far apart. And when they're close together, that's where you hear those initial pops. And then when they're far apart, that's the quiet between the pops. And so as the oval shrinks, the pops get closer and closer together. And then eventually it starts to sound a lot like the first one. And if you listen to those back to back many times, you'll actually hear that even near the end, they sound different. And that's because the orbit maintains some of its oval shapedness as it approaches the end. Okay? Okay, so let's just talk a little bit about ultra compact binaries, and we'll take the end of the talk here. So this is what my group actually works on. So we are responsible for simulating the stellar graveyard of the Milky Way. And as I'm sure most of you have been taught or know, especially if you're double star observers, there are lots and lots and lots of double stars in the galaxy, actual binaries where the stars are bound to each other. Estimates range from 40 to 60%, depending on who you talk to. But those stars, just like all the stars, eventually die. And when they die, their stellar skeletons, typically white dwarfs, because those are more dominant than neutron stars or black holes, still remain together. And when that happens, you get these, as we call them, ultra-compact binaries. Two white dwarfs, two stellar mass objects the size of the Earth in very short period orbits, orbits in the range of 15 to 30 minutes or so. And there are some 10 million of those in the Milky Way galaxy. And so what we do in my group is we simulate the stellar graveyard of that Milky Way galaxy, and then we take that simulation and we push it through our LISA analysis software, what we'll use to analyze real LISA data in order to try and understand what secrets of the Milky Way can we learn by observing the stellar graveyard. Okay, so here is a movie that a colleague of mine made from our data. Flying outward from the sun, showing all of the white dwarf binaries that LISA might detect. And what you'll see is once you get all the way out to the great distances from the Milky Way, we can see the stellar graveyard through the entire Milky Way. There is no zone of avoidance. There's no obscuration by dust or anything along the plane of the galaxy. Gravitational waves pass right through that. So we can actually map out the entire structure and shape of the Milky Way. In this movie, you'll see a couple of different colors. The black dots are known white dwarf binaries we can already see in our telescopes that will be LISA sources. The red dots are all of the individual white dwarf binaries in the stellar graveyard that LISA will see. And then the purple dots are a collection. There are maybe hundreds to thousands, depending on the size telescope that you want to use, of white dwarf binaries that we can see both with LISA in gravitational waves and with telescopes at the same time. And these are extraordinarily important sources because they will give us ways of probing the stellar evolution of the stellar graveyard, the mass properties, the accretion properties, the radius properties of all of these white dwarf binaries in ways that are almost impossible right now with ordinary telescopes. And not just because it's hard to observe these things with ordinary telescopes, but Lisa's going to put thousands of these systems on the table. So we'll have many, many examples that we will be able to observe and look at. The black dots are important ones, and I'll bring them to your attention because these are the known binaries. And probably the most famous of these is a star called AMCVN. It's a 14th magnitude star in Canis Venatici. And everything we know about that white dwarf binary, we learned from the amateurs. The period of that binary and the fact that it is a gravitational wave source is something that the amateur community worked out. A group that Joe Patterson at Columbia shepherded in the 1990s called the Center for Backyard Astrophysics was the first group to measure those binaries for us and get the parameters that we use for AMCVN today. So, so there will be many opportunities for those of us who are amateurs who do photometry, and in particular like overlapping our hobby with science, that there will be some of these LISA sources that we may be able to observe at the same time. Another thing that we do in my group is we study how the properties of the Milky Way, which are very poorly constrained, affect the shape and size of the Milky Way. And so right now what you see us doing is we've made two versions of the Milky Way. We've evolved two versions of the Milky Way on the computer and asked which one, how does Lisa see them differently? You'll notice the one on the left looks fat, and the one on the left looks thin, and the one on the right looks fat. And the changes there have to do with the history of stellar evolution in different parts of the galaxy. And what you'll see is it's very prominent in Lisa's data that one of them has a different stellar evolutionary history than the other. So this is another example of something that we'll be able to do with Lisa when we have that Lisa catalog finally in our grasp. Okay? So the last sound I want to play for you, and then we'll wrap up. This is a sound that represents all of the Lisa data together. That's all the gravitational wave data that Lisa's going to be constantly bombarded with. You'll remember earlier I said that the LIGO sources are transient. They kind of appear, LIGO detects them, and then they disappear. Lisa sources aren't that way. Lisa sources are persistent. They're always on, and they're on the entire time that Lisa flies. And then sometimes some of them disappear. They go through that chirp that we listen to, but then all of the other sources are still on. And so the way we describe this to people is we liken it to hanging out in the planetarium before a show starts, or in the lunchroom when you're at work. Everyone's always talking at once, and you can hear everyone talking at once, but you can't make out all the conversations. There's a general hubbub, or as we like to say in gravitational astrophysics, a confusion of astrophysical noise. All the gravitational wave sources, or all the conversations, going at the same time. But above that, you can hear individual things. You can hear loud people talking very loud. You can hear people very close to you talking loud enough that you can hear them and make them out above the hubbub. Okay, so this sound has a whole bunch of overlapping Lisa sources. It has the galaxy, it has black hole binaries merging, it has some emeries in it. It's a little bit quieter than the previous sounds I pushed you, so if you can't hear it, you may need to turn your speakers up a little bit. But it goes for about 90 seconds. I'll probably only let a minute of it play until the first black hole merger. But I wanted you to hear the cacophony, and then we'll wrap up for the evening. So there's the first black hole. There's another one a little bit later on. But you should hear this kind of general scratchy chirping, and that's all the white dwarf binaries talking at the same time. And it goes on and on and on, okay? It's very tinny. It hurts your ears a little bit, but if you listen to it in headphones, you can do that exercise where you pick everything out. So the last thing that I want to say is that science is a universal endeavor. It spans across institutions, across countries, across states, all around the world. And all of the great discoveries that you hear about today are almost never accomplished by a single person. We have extremely large teams of people building spacecraft and designing lasers and writing computer software and teaching the next generation of students who are going to work on this science for the next 20, 30, and 40, and 50 years. And so we can't do all the things that we do in science without these enormous teams of people. The LISA consortium, of which I'm a part of, is about 1,500 scientists around the world. That does not include all of our colleagues who work at ESA, at NASA, who do the engineering to build the spacecraft at the various aerospace companies, and so on. But we can't do gravitational wave astronomy, even on the ground. LIGO's the same way, without thousands and thousands of people involved in this. And so when you hear about the things that are going on, in all likelihood, there's someone very close to you in your sphere who's connected in some way to one of these scientists doing one of these great scientific things that you hear about in the news. I would be remiss if I didn't point out that I also work with a very large group of people. My faculty colleagues I work the most closely with are there across the top. Vicky, Matt, Brett, and Patty are the four that I work the most closely with. And then everyone down at the bottom are students who work in my group. There's a couple undergraduates, but mostly graduate students who are doing their PhDs and master's degrees with me. Two of them there, Katie Brevik and Michael Katz, have graduated in the last 2 years, but they still collaborate very closely with my group. And my cat is always there in the scene as well. So I always like to leave you with something to read. So here's a few books. There are starting to be more books on gravitational waves that you can find. This book by Marcia Bartusiak over here on the left is a really excellent one. There are 2 editions of it. One came out before the LIGO discovery, but one came out after the LIGO discovery. So if you want to read about the first discovery, you should certainly find the second edition. Brian Clegg is a very good science writer. I think he's probably more well known in Europe than he is here in the United States, but this little book on gravitational waves I think is eminently readable. And then Kip's book over there on the right, both Kip's and Marcia's book have won science writing awards. It's kind of a more general relativity style book. It's about black holes and time warps and wormholes as well as gravitational waves, but if you're interested in that sort of stuff, it's probably the best book out there at the public level. If you'd like to do some citizen science related to gravitational waves, you can join us on our Gravity Spy project. That's a project that we developed here at Northwestern in collaboration with our colleagues at the Adler Planetarium in Chicago and the folks at Zooniverse. Some of you may be familiar with Zooniverse. There are many citizen science projects that you can join at zooniverse.org. And then there's a series of links there to various YouTube channels and my blog and stuff like that, that you can certainly learn more about all of this stuff. So I am going to end there and say thank you very much for your attention. I'm glad I had the opportunity to come chat with you, and I will pass it back to my hosts to take questions or move on per their desires.
Questions. There's got to be questions. There's got to be questions.
Shane, I've got a question. How
do
you focus LISA on a particular object in the sky you're interested in observing?
That's a great question. So actually, let me reshare my slides again, because I think it's probably helpful to do that. Because I want to go back to that movie I showed you of LISA's orbit in order to do that. So if I go back to, whoops, I should have picked the slide first. So if I go back to this movie. Okay, so you see LISA going around there. So remember I said that LISA's sources are persistent. So let's imagine that this star, right, can you see my mouse? If I run my mouse around, okay, yeah. So imagine that star is the one that LISA's observing. So what you see is sometimes LISA's moving away from that star, sometimes it's moving towards that star, sometimes it has its backside to the star, sometimes it has its side to the star, sometimes it has its front side to the star. And since that star is always on for the entire year that it takes LISA to go around, we can use that changing perception that LISA has of the star to point to where it's at. So a way to demonstrate this for yourself is to get your roommate or your spouse or your kids to stand in the middle of your living room and sing a song or hum or make some noise, and you close your eyes and walk around the room. And what you'll find is that as you walk around the room, your changing profile of that person is something you can point at, that you can very accurately point at where they are by simply moving where you are, even though you have your eyes closed. Another way to do that with a group of people, this is not safe if you don't use the right lasers, but we often do it. We'll give everyone a laser pointer, have everyone stand in a random place in the room and close their eyes. We'll have a volunteer, Derek or someone, walk to some random place in the room and say something, and everyone shine their laser pointer to where they thought the sound came from. And what you find is some of the laser pointers are off, but most of them kind of converge to the same spot. And so this is really what we're doing when we point LISA, is we're triangulating based on the fact that we observe this object from different places along LISA's orbit.
So it's sort of a parallax computation.
Yeah, it's more Doppler shift than parallax, but it's essentially parallax in a slightly different way. That's a good question.
Yeah, with safe lasers only. I like the idea of that.
Yeah. Only use eye-safe lasers for that experiment.
Everybody point at once, vaporizing.
Or wear laser goggles, I guess, right?
Yes.
Yeah.
Anybody else? Just speak up.
I had a question about the spectrum of the gravitational waves.
Okay.
And how it, so I guess instead of how with light, you know, you can kind of determine distance by like the red shifting or like what direction an object's moving into with the blue shift. So in the wavelength of the frequency of the gravitational waves can tell us more of like is it the same idea like distance, or it's like more like time, like how long does something take to make a movement? Is that what you were kind of trying to?
Yeah. So are you specifically interested in how do we measure the distance to sources?
Not so much the distance, but like what exactly is the frequency telling you? Like I noticed that colliding black holes have a very high frequency, right? Because they're moving so fast, right?
So let me go back to the spectrum graph and point you at something very specific, which I went over really quickly, so it probably wasn't as clear as it could have been. So here on the spectrum graph, you'll notice that I put on the bottom there the frequency number, okay? And so those of you who remember your physics will know that light can be described either in terms of its wavelength or in terms of its frequency. The two numbers are related by the speed of light, and the exact same thing is true of gravitational waves. Okay, so what astronomers measure, what I measure with LISA, is that number, the frequency. But the top row where I wrote period is the astrophysical time. And so for binaries, for circular binaries, the orbital period or the orbital frequency is exactly twice the gravitational wave frequency. So if I can measure the gravitational wave frequency, which I can, that's the whole point in my measurement, then I know exactly what the astrophysical time scale is.
Okay, I see. That's super interesting. I can see how that'd be so useful. So if you have like, for example, on the red shifted so does that mean that the like each frequency pulse would only be like detected over the course of that many, like that much time?
Yeah, so there's two sources of redshift we have to deal with, right? So one is the Doppler shift, which is both blue and red, associated with LISA's motion around the sun. Okay, so that, right, NASA and ESA monitor and they tell us, here's how LISA was moving, so we can subtract that out, okay? But for things like black holes, which are very far away in the universe, the gravitational waves also experience cosmological redshift, just like light does. And so we have to account for that fact. Otherwise, our measurements will be off. But the advantage we have, like, so electromagnetic astronomers, they deal with this because they're looking at known spectral lines. They look, so if you look at hydrogen, say it has 2 or 3 or 4 lines that you're measuring, that hydrogen emits. And when those lines are redshifted because of the traveling of the light through the universe, all of those lines move together as a family. So that's how we measure the redshift with ordinary telescopes. We look for the family of lines and we say, how far did it measure? For LISA, we don't have lines that way. But what we do have is that all of the quantities that describe the source, so the frequency is one of them, that's what you and I have been talking about, but also the masses and the other parameters that we measure for the system, all of them also experience redshifted factors that electromagnetic astronomers don't have to pay attention to, but we as LISA gravitational wave astronomers do. And if we don't, so the way our equivalent thing of having a family of lines is all of those quantities have to change in a consistent way in order for us to measure the redshift. The masses have to change in exactly the same way that the frequency has to change. It has to be consistent with the distance that the source is. So that idea of having a set of measurements that together all tell you the same redshift is still true for LISA.
Okay, very cool. So you have basically an extra layer of data that you can now even more precise, because I know measuring distance and measuring things like that using just the techniques that we already is already difficult. So now you can be more precise. Wow, that's so cool. Oh,
and there's really cool science. There's really cool science to do if you can see one of these sources, both with telescopes and with LISA, because you can use that cosmological information from the two of them against each other in order to decide, what's making one of these measurements hard, or how well do we know the number, or is there something weird going on? So that's actually something we're really excited about being able to do.
Okay, that's very cool. Since I have you, can I just ask you one more question?
That's up to the protocols in your club.
that's fine.
Everyone's going to tackle you and slap you about the years, maybe not.
I just wanted to ask really quick, because you mentioned that like you're predicting that we'll be able to finally see stars and objects that are on the other side of the galactic core. What about beyond the CMB? Like, could we look all the way back to a lot closer to the Big Bang?
Yeah. So the experiment that is doing that are my cosmic microwave background colleagues, which I just mentioned in passing on the spectrum slide there. So the gravitational waves that they are searching for come from that time before the cosmic microwave background was emitted. So as we say, before recombination. Those gravitational waves are generated in the very early universe. Because gravitational waves don't interact with matter, just like I said, the gravitational waves propagate through the galaxy without being impeded. They propagate through the very early universe without being impeded as well. And so they're really the ones who are going to be able to make that measurement. For things for LISA, there are not sources like you and I have been talking about. There aren't black holes in the time before the cosmic microwave background, because the universe was this morassy soup of energy and subatomic particles. But the gravitational waves from that era will imprint themselves in the cosmic microwave background, and that's what our colleagues at the South Pole are actually looking for.
Okay, very cool. Thank you.
And I wrote about this. There was a measurement they made a couple of years ago, which we've now refuted with data from one of the CMB satellites, Planck. But I wrote about their technique and their method on my blog if you wanted to go read a little bit about how they do that. So,
Robert Vogel had a question. He wanted to know, when will LISA be launched?
So right now, LISA is going to be launched probably in the early 2030s. So I don't remember exactly on ESA's schedule, but you know how launch dates are. But 2030, 2032, somewhere in there. So.
Okay, a little ways out still. Cool.
So right now, what's happening is our industrial partners, or a pair of industrial partners, are working. They've taken the design from us scientists, this spacecraft and what it has to do and what we've calculated about it. And they're off at Walmart seeing how much screws and duct tape cost and redesigning the spacecraft. And so next year they will come to the table with the design, and that will go to the space agencies. They will select the design that we want, and then we will start building and bending metal in the next 2 or 3 years. So.
Cool. Anyone else? All right. Well, I want to thank you, Dr. Larson, for coming on.
Thank you, everyone.
Yeah, very interesting. I love the visualizations too. I'm into that. But I didn't want to. I didn't want to I'd get way off topic asking about those.
Well, we can talk about those offline if you want to send me an email. So,
okay.
Thanks, everyone.
All right. Thank you. All right. So next up is our how to do winter solstice calculations with John Pinto. If you're ready, John.
Sure, Richard. Just make me present.
Okay. Can I do that, or do I need Derek or Frank? They can probably do it by the time I find the right thing to click. John Pinto, co-host. You're good. Share your screen and run.
Cool. All right. You should be able to see what I'm doing.
Yes.
All right. So we are going to calculate the winter solstice. That is obviously a very northern hemisphere way of talking about it. We probably should really call it the December solstice, because down in South America, this would be the summer solstice. This is what you're going to need if you want to follow along with me. You're going to need a pen, pencil, and a piece of paper. That's really all you're going to need, unless, of course, you want some optional tools. I actually use the item on the right for this exercise. I will have to make some assumptions just so this talk doesn't take 3 hours. We can maybe do some other minis on some of these items that I'm going to talk about. So, of course, this is mostly going to be about math. So if you are a math phobic person, you probably want to hide your eyes and mute your audio. However, from an astronomical point of view, there are some things I'm just going to assume you know what I'm talking about. First of all, you need to know what a constellation is. I'm going to mention Scorpius and Sagittarius during this mini program. I'm also going to be talking about something called UTC, Coordinated Universal Time, because again, that comes into the part of the calculations. I'm going to mention the celestial equator and ecliptic only because they're used to define how you figure out what the solstice is. Declination and longitude are also important things to know about. This is probably the most important thing, which some of you may know what I'm talking about, and probably most of you don't. Julian day numbers. I'm also going to be talking about sextants for those of you with a naval background. And of course, I'm going to be presenting this from the point of view of an observer in Florida. So there'll be some assumptions I make about time zones and things like that. So what is the winter solstice? There are a number of definitions you've probably heard. For example, there is the common definition. It's the day with the least number of daylight hours. You've probably also heard it's the day when the sun reaches its southernmost declination at noon. And then there's what I'm going to call the astronomical definition, which is what our calculation is going to be based on. It's the date and time when the sun reaches 270 degrees of ecliptic longitude. Basically, it's the time when the sun reaches a certain point that is currently between Scorpius and Sagittarius. Now, all of these definitions pretty much correspond with one another within a few hours. The reason for the astronomical definition is because it's something that's easily calculated. For example, the common definition of the least number of daylight hours, if you were to actually measure with a watch the number of daylight hours around the winter solstice, you'd get pretty much the same time for a few days before and a few days before and after the solstice. So it's not that accurate. Similarly, for the southernmost declination at noon, again, a few days before and a few days after, even with a sextant, you probably would not be able to tell the difference. So that's why we use the astronomical definition, because that's something you can actually calculate fairly accurately. And of course, that's the definition we'll use. We are going to use a simple approximation. I'm not going to give you 72 different polynomial coefficients. You're going to see it's actually fairly, very simple. And this approximation is actually accurate from about the year 2000 until about the year 2080. And I hope that's long enough for most of us that we need to calculate this. And our accuracy is actually going to be within 20 minutes of the actual high accuracy value. So if all you're really looking for is what day is the solstice, this is definitely going to tell that to you. And you'll even get close enough to the hour of the solstice. All right, so how do we do this? We're going to take it in 3 steps. So the first thing we're going to do is we're going to calculate the Julian day number of the winter solstice. Turns out that that is actually the simplest part of this entire calculation. Then we have to convert that Julian day number to the UTC time and date. And finally, we'll convert that UTC time to our local Florida clock time, or sometimes called LTC, LCT. All right, let's get going. So calculate the JD of the winter solstice. Here's the magic formula. That's it. You take that large number there and you add a slightly smaller large number and multiply it by something called the MF, or what I call the MF. What is the MF? MF is, you take the year, say 2020, take the last 2 digits, XY, and rewrite it like this, 0.0XY. So let's take our example for 2020. MF is 0.020. We're going to stick that MF into this formula, and we're going to calculate a JD number. So that's the substitution. That's the result of the multiplication. And that's the result of the addition. So that is when the winter solstice will occur in 2020. I do want to mention one thing, if anybody can guess what the MF stands for. It actually is a millennium factor. Not the Millennium Falcon, not the millennial factor. It's the millennium factor. All right, so now what? You just need a JD calendar, and you will know exactly when the winter solstice occurs. And the AAVSO nicely gives us a Julian day number calendar. You can go on the AAVSO website and you can actually print out an entire year of your Julian day numbers. So if I go back one screen, you'll see this Julian day number ends in 9204. I look at my Julian day calendar, 9204 is December 20th. So this is telling us that the winter solstice is going to occur in 2020, UTC time. That's what JD is always related to UTC. Sometime between noon on the 20th and noon on the 21st. So somewhere in there is when the solstice is going to occur. So how do we actually calculate that? So we have several options. As I mentioned, you can just consult the Julian day calendar, and if you're good enough to say, well, it's from this date to this date, and I'm happy with that, you're done. You can also use the online JD to UTC calculator. At that same AAVSO website, they actually have a nice little calculator, and I will show you a screenshot of that. Or you can manually calculate the UTC, which is what we're going to do in the next few slides. just for those who are interested, this is what the AAVSO JD to UC calculator looks like. You can either put in a JD number like we have, click convert to UTC, or if you want to go the other way, you happen to know the UTC and you want to know the JD, you can do that as well. Or you can just, if you're interested in what the JD is right now, click this bottom button. All right, so I break this piece up into a couple of parts only because I find it easier to think of it this way. So the first thing I like to do is calculate the JD for the beginning of the year, or what I call year.0. So this is the calculation to calculate the JD for the start of the year. So you take this large number, and then you take 365.25, the length of the year on average, times your year minus 1. Whatever that comes out to, you truncate that, you just drop the fraction, add it to this number, and that gives you the JD for the beginning of the year. So again, take an example for the year 2020. Here's our substitution. We're stuck in 2020 minus 1. Did the subtraction. We've done the multiplication. We've done the truncation. And we've done the addition. So that is the JD for the beginning of the year 2020. And you're going to see why that makes a lot of what we have to do a lot simpler. Okay, the next thing we want to do is find the JD for December. We all know that the winter solstice occurs in December. So we now want to find out the JD for the beginning of December. Again, it's really simple. You take the JD of the year that we just found, and we add something called the days into the year for the beginning of December. And that number is either 334 if it's not a leap year, or it's 335 if it is a leap year. And everybody knows a leap year is a year divisible by 4, at least for the time frame we're talking about. Again, we'll take our example, 2020, it was a leap year, so our days into the year was 335. We add that to the JD we found for the beginning of the year. And we find this is the JD for the beginning of December. Now we're pretty much almost there. Now we're ready to calculate the UTC of the winter solstice. So since the UTC is in December, we know that part's simple, right? We just need to calculate which day and time in December is the winter solstice. And that's just the JD we calculated all the way at the beginning, and we subtract it from our December JD. So again, for our 2020, this was the number we had calculated for the winter solstice. This is the JD for December. So the UTC is 21.4143298. And now all that's left to convert it to Florida time. Florida time is basically the UTC minus TF, or our time zone factor. So for Florida, our time zone factor is 5/24 if we are in standard time, or if certain people get their way, December will be in daylight savings time, we would use 4/24. But we're standard time, so it's 5/24. And that's the fraction for 5/24. Again, we'll take our example for 2020. That's our time zone factor. That's our subtraction, so to calculate the LCT. And so in Florida, on the 21st at 0.2059965 hours, it will be the solstice. Now, of course, not all of us have a clock that works on fractions of a day. We now have to convert that to a standard 24-hour clock. Now, this next calculation is probably familiar to most of you, but we're going to go through it step by step anyway. I'm not going to do like, this is the formula and this is the calculation. I'm just going to do the calculation because I think it's going to be fairly obvious how you do this. Again, we're taking the year is 2020, the month is December. So to get the day, you just truncate that LCT number, and so it's December 21st. You now need the fractional portion of the day, so you subtract out the day from your LCT, and you get the fractional portion. To get the hour, you multiply it by 24, the fractional hour, I should say. And so you get this 4.9 number. To get the hour, you truncate that. So we're at 4 hours, December 21st, 4 a.m. We need the fractional minute. So we should subtract the hour out of there. This is the fractional minute of the hour. And to get the final minute, you take that fractional minute, multiply it by 60, just did substitution there. That's the result of the multiplication. And then you just round it, which is 57 minutes. So for Florida this year, winter solstice occurs sometime around December 21st at 4:57 a.m., plus or minus 20 minutes. As I said, this is not exact. I did look up what the actual high accuracy number is, as at least published by Sky and Telescope. And it's December 21st at 5:02 a.m. So we were pretty darn close. Okay, so I have made a slide here that has all of the calculations all in one go, and I've marked it 1, 2, and 3 for the 3 steps. So that was your first step, your second step, and your third step. So if you ever wanted to run through this again on your own, you could just basically take this slide and just plug in the various numbers that you need. If you want to learn more on your own and become way more versed in this than I am, this is a great introduction book. It actually is a gentle introduction to doing computational astronomy. I highly recommend it. It's a fairly new book. I think it's still in its first printing, so there are a bunch of typos in it. And I suggest you go to the author's website, which he lists in the book, so that you can mark up your copy with the corrections as we find them. Next in order of difficulty, this is a really famous author, Peter Duffett Smith. As you can see, he's already in the 4th edition. I actually started with his first edition back in the 1970s. Unfortunately, I don't own that first edition anymore. It's actually highly prized. I do have the 2nd and 3rd edition. So this is a great book, and it comes with spreadsheets, so you can actually run these calculations yourself. Of course, everybody knows the handbook. If anybody does any kind of astronomical calculations, genius. In fact, most of the calculations I took for this slide come from this book. And then finally, there is something everyone calls the reference. I think Richard just got himself a new copy of this. This gets into all kinds of interesting things, like how to take into your calculations general relativity and the adjustments that it comes in. So way, way more advanced than I probably will ever need. For your viewing pleasure or calculating pleasure, I have included all the other JD calculations for all the other events in case you want to get started on your 2021 calculations. And I've given you all your days into the year values for each of the months. So again, you can do this all on your own. And with that, I am done. You can unmute your audio, uncover your eyes, and I can take some questions.
Any questions for John? I'm just going to jump in and say this is when I first, I'm a software developer by trade. And when I first started learning to program, Gene Neese's book was my motivation to stay up till midnight typing things into my computer to calculate this sort of thing. And I just recently got all the calculations right for the lunar librations, and I am not going to go over that math with the club. You're welcome. Okay, if nobody's going to jump in, thank you very much, John, for sharing that. Basically, you know, this is a good time to sort of make an interjection. This is the Central Florida Astronomical Society. It is populated by amateur astronomers. Many of us are interested in observing. Some of us are interested in doing other types of astronomy, mathematical astronomy, modeling, astronomy history, observing programs. For me, it's lunar theory. I know a lot of people think it's astrophotography, but my actual science interest is in lunar theory. So, if you have an interest in astronomy, well, hey, join the astronomy club. Well, you've already done that. Congratulations. Tell us about it. Put together a little something, and you may find that, your family pokes fun at you. I'm sorry to say that, but mine does. They do it in all in good fun. But, you're not alone. There are other people who share your interests and passions too, and it's great to have that kind of a brotherhood or sisterhood, so to speak. So thanks again, John, and I hope again to encourage anybody else who wants to contact Tricia, our vice president. She's in charge of our programs, and she will talk to you and even mentor you if you need to, and put together a little program for us.
Richard, I did want to say one thing. I am going to upload that slide deck to Groups.io and to
Okay, great.
our Facebook files so people can go through it on their own.
Okay, great. Thanks. And I skipped over the member photos and sketches, but Derek is up next anyway with tonight's sky and his talking about the Jupiter-Venus conjunction. So Derek, if you want, you can just do both of those all together or back to back, however suits you.
All right. Hello, everybody. As you can probably see, I'm actually in my office right now. I've been doing virtual school programs all day, pretty much every day, it seems like, for the last couple of weeks. So I've actually been in the planetarium. The planetarium misses you all, and hopefully at some point we will get to join up on a meeting here physically at some point. But what I'm going to do now is I'm going to go ahead and share my screen, and we're going to take a look at some of the photos that have been submitted to me this month for the Astrophotography Showcase. We also do have a couple of, actually, I think we have one sketch this month from our famous sketcher, Bill Castro. So let me go ahead and share my screen here, and we'll get started. So again, if you happen to see your image on the screen here, just go ahead and unmute yourself, and we would love to hear a little bit about what your image was, what you take it with, any other information that you would like to share with everybody in this meeting. So the first image, actually, we're going to talk about some sketches. This is Bill Castro's sketch of the Kemble's Cascade. It's a beautiful cluster of stars here. But I'm going to let Bill, I believe he is on here, I did see him, talk a little bit about not only the sketch that he made, but also his collaboration with a friend of his in Ohio, I believe.
Hey, Derek. Yeah, I first drew it, as you can see in the upper left. I was wondering how well I did my orientation and all that. That's with my 130 millimeter refractor. And then I went out the next day. I thought, well, I should have just focused on the open star cluster. You see the chain of stars that goes down to the open cluster 1502 in the bottom. So I did a high power sketch on that, which is below. And then I got with my old buddy I used to work with up in Ohio and had him image that. And he's got a 127 millimeter refractor that he used. He got two frames on his camera, and so you see it kind of matches pretty good. But the image is really super. Work a little bit on my star placements and all that, but it's amazing what he can do. He's in Stowe, Ohio, and Stowe, Ohio is a little bit north of Akron and south of Cleveland. And so he's working with more light pollution than what I'm doing in Oviedo. He's probably one magnitude less. than what I can see. Excuse me, naked eye.
Excellent, excellent, Bill. Yeah. Now, of course, for those that are imaging, interested in imaging, star clusters are a great groups of targets to photograph, even in light polluted skies, because when you do your post-processing, you can eliminate a lot of the background, light pollution and stuff like that. So don't discredit star clusters, like open star clusters and of the like, in light polluted environments, because you can actually do pretty good with these star clusters, even in very light polluted areas like Akron and other areas similar to that. So great work. Now, I think it was fantastic, Bill. I think this looks really great, and of course, you definitely have done a great job at doing a sketch on this. So thank you for sharing that with us this month. Okay, the next picture was submitted by John Pinto, probably during his latest astronomical calculation of the orbit of Mercury and Venus, I believe, right, John? But do you want to talk a little about this?
Yeah, that's coming up in a future mini program. I had a little quick vacation with my wife to Savannah, Georgia, and it just happened to be when Mercury was pretty visible in the morning. This was a fairly bright location where I was, as you can see all the lights. It was actually just behind the parking garage where I had my car. As I ran out early in the morning while everybody was sleeping, and I just happened to catch Mercury peeking up over that building. And that was just taken with my iPhone 6S Plus, nothing really fancy. I did use Pro Camera so that I could manually control the focus and the exposure to at least try to possibly get Mercury, and I was lucky to get it in there.
Great, yes, of course, John, that's great, and that was a really fantastic time to see Mercury, and glad that you were able to catch it in this parking lot area. So, and of course, the iPhones and other smartphone devices are getting better and better with taking images of the night sky. So it's pretty cool that we're able to do that. All right, this next image is from Andy Sova. Andy, do you want to talk a little bit about this this image you've taken here? I believe Andy was on earlier. I thought I saw him on there. Well, this is of course many of you recognize this object. This is the famous Orion Nebula and Running Man Nebula, M42 and M43. And I believe he mentioned that he took this with his William Optics GTF-81 refractor telescope. I unfortunately didn't get the information on his image, or excuse me, on his camera, a sensor that he used, but it's still a very nice, clean image. And one of the things that's actually difficult when you image the Orion Nebula is the central part of the nebula is usually blown out when you expose for the fainter details. And Andy was able to process both a shorter exposure and a long exposure to get that nice dynamic range between the trapezium here and the outer areas of the nebula. So great job, Andy. And I believe the next image is also Andy's as well. He's been spending a lot of time in the constellation of Orion, looking at, of course, here we have the Flame Nebula and the Horsehead Nebula. And I believe it's the same telescope that he used. Unfortunately, I don't have the details on the camera sensor, but a great job imaging this site here. Now we are getting some comments. Maybe he is chatting. Let me just make sure. Okay. All right. Nope. No information about the images on there. Just wanted to make sure. And our final image of this evening is an image I took of the Crab Nebula. This is taken with my 190 millimeter Mac Newtonian reflector and a Canon 6D cooled camera on a software-based Mighty Mount. This is over at Geneva. I had a chance to kind of play around with my new mount and trying to do a little bit of unguided work here. So this is actually pretty good for unguided skies. And And yeah, so this is actually fairly cropped. The Crab Nebula in my field of view is very small, so this was heavily cropped there. But you can see the details of the supernova remnant here. So now, hopefully, as you know, there are expected to be some nice clear skies in the next couple of weeks. So I suspect, and I would hope to see more astro images for the upcoming months. And what we're going to do now is I'm going to go ahead and stop my share for just a second as I pull up the next window, which is Stellarium. And I want to actually talk about a few things that are coming up here. I'm actually going to, now originally I was going to talk about the conjunction by itself, but I figured there was some discussion earlier in the chat about the Geminid meteor shower. And the Geminid meteor shower is happening, actually it should be happening right now. But the peak of the Geminid meteor shower is actually the morning of the 14th. Don't go the night of the 14th. You would want to get set up on the evening of the 13th into the 14th, which would be a Sunday into Monday morning. But what we're going to do is we're going to go back in time just a little bit here to the 14th. And what you're going to do is, in order to see the Geminids, first things first, the reason why they're called the Geminid meteor showers, because the radiant, essentially where the meteors will be radiating from, comes from the Gemini area of the sky. However, you will see meteors streak across the sky even as early as sunset. However, in order for it to be a Geminid, it has to be shooting from the radiant point of Gemini. So, for example, if you look to the east and the meteor is streaking towards the west, that could be considered a Geminid. If it is shooting towards the southeast, it could be a Geminid. If the meteor was shooting towards the east, it is not, and Gemini is not up in the sky, then it is not a Geminid. Now, if Gemini were up in the sky and it shot below Gemini, it could very likely be a Geminid. So just to give you an idea, I've been seeing a lot of images of people taking photos of what supposedly are time-lapse images of meteors. A lot of them are what we call sporadics, which are just basically meteorites or meteors that we see just sporadically in the sky. Now, of course, Gemini starts to rise later in the evening, so about 8:40 or 8:30 or so, we'll start to see the constellation of Gemini emerge over in the east. A best way to find Gemini is to look for Orion. Of course, 3 stars in Orion's belt here. We have the bright star Betelgeuse. And what we're going to do is, what I like to do is Rigel, which is the bottom right star of Orion. We have Omnium, which is the middle star of Orion's belt. And we have Betelgeuse. We take these 3 stars and we basically point them towards the left, and we'll come across these 2 stars here. We have Pollux and Castor. These are the heads of the Gemini twins. And essentially at that point, we'll start to see more and more meteors. Now, when Gemini transits at the meridian, that's when we would consider to be the true peak of the Gemini meteor shower, which will occur roughly around 1 o'clock in the morning. And that's when you're going to have your greatest extent of meteors during that meteor shower. Now, a couple of years ago, some of you got a chance to watch the Gemini meteor shower after a CFAS holiday party at the Geneva campus. And if you stayed up as late as some of us did, we saw over 180 an hour. This is a wonderful meteor shower to view. And the best part about it is we will not have a moon up in the sky for us to deal with. So we are going to have a nice, dark, clear sky, or hopefully clear skies. Right now, the weather forecast shows in Central Florida to be partly cloudy to clear on Sunday night into Monday morning. So we're going to keep our fingers crossed and hope that we will see the Geminids. Now, I want to let you all know that right now I am planning to head over to Herky Huffman Bull Creek to do some Geminid meteor shower viewing. The other option I'm thinking, depending upon the weather forecast, is I'm also thinking about heading up to Farrell's Lake over in the Ocala National Forest. If you are following us on the groups.io or the Facebook page, I will be making an announcement of which location I will choose to go to later this week. If you would like to join me and a social distancing Geminid meteor shower viewing, I will let you all know. At the moment, those are the 2 locations that I'm currently looking into, so I will keep you all up to date. I might also send an email to Sharifa that she can send out to the membership to let them know which location. I hope to know by Friday when I will know for sure which area will be the best for observing. Both of those locations will be premium places and are open 24 hours for us to observe the sky. Now, the next thing I want to talk about is an event on the solstice. Yes, on the solstice, we have a very special event going on. So every 20 years or so, Jupiter and Saturn, based on their orbits, will produce what we call a conjunction. Conjunction is basically when planets essentially line up in the sky. This happens every 20 years. However, the last time that both Jupiter and Saturn have been less than 0.1 degrees in the sky, that's about 1/5 of the size of the moon in the sky, was back in 1623, only 15 years after Galileo looked through the telescope for the very first time. And so this is a fairly rare event. It doesn't happen very often at this type of distance towards each other. And some people will say that depending on your eyesight, looking towards the southwest on the 21st, you will see over in the southwest, right after sunset, a kind of oblonged, kind of football-shaped star where Saturn and Jupiter are merging. However, you will most likely see Jupiter with an extremely small star next to it. And to give you an idea of the distance between these 2 objects, it's more similar to Alcor and Mizar found in Ursa Major or the Big Dipper. And so that kind of gives you more of an idea of the distance between these 2 stars. So whether or not they'll actually be physically merged, probably not. I don't think so. But depending on your eyesight, if you can't really discern those double Alcor or Mizar, they may appear to be kind of more of a blurry kind of football star. Is it a Christmas star? Well, I would call it more of a solstice star. But in reality, they're going to be 2 very, very close objects. Now, the more important thing is what are you going to see through an eyepiece? Well, we're going to zoom in towards Jupiter and Saturn. So we're going to zoom in here. And the coolest part about these objects, let me go ahead and stop time here. Yes, we have the ability to do that. With this field of view, remember, we're looking at 1/5 of the size of the moon in the sky. So if you have a fairly good, decent eyepiece with a great field of view, maybe a 26 millimeter, a 25 millimeter, depending on your scope that is, you should see both Jupiter and Saturn in the same field of view. This is going to be an absolutely incredible experience to see both the planet Jupiter and Saturn together with all of their moons. Now, we are actually going to be hosting a virtual event. And right now, me and Frank, who are going to be leading that, and we're hoping to have some others just in case of inclement weather with our luck. Justin has left Florida, so his Q powers are not as powerful as they usually are if he was in Florida. But we're hoping for clear skies. And if we do have clear skies, we're going to be able to do a virtual viewing of these objects. Now, the other thing is we're hoping to have others to help us. Now, here's the interesting thing. We're going to actually be doing this on Zoom webinars. I'm going to, at the very end of my program, I'm going to be posting a link to the registration page. You can register, and you'll be able to get an access link to the page that you'll be able to log in on the date of December 21st. We're also going to be doing Facebook Live, but some of us aren't exactly too keen on going on Facebook and watching it that way. So we are going to be doing something new this time. We're actually going to be doing it through a webinar feature, which, by the way, is what we're hoping to do going forward in our CFAS meetings. So this is kind of like a beta test for that. But me and Frank tried it out today, and it works really, really well. So we're looking forward to offering these in future events for people to join instead of having to watch on Facebook. But this is essentially what you're going to see. Now, here's the fun part. Again, conjunctions like this happen every 20 years. Well, in 2040, we're going to have another Jupiter-Saturn conjunction on Halloween. Yes, folks, October 31st, 2040, we're going to have another pretty cool Jupiter-Saturn conjunction on Halloween. So that means that it's not going to be as close, but to most people, it will be close enough. So this is actually a very exciting event. And I would say, even though 2020 has been what I would say has been a really bad year, at least from astronomy point of view, it's actually been a fairly fun year, at least for observing. So thankfully, we have something to look forward to at the end of this year. So hopefully you get to join us virtually, or you get a chance to observe these objects in the sky. And this, by the way, is my only observing challenge for this month. My observing challenge to you all is to observe this fantastic conjunction with your telescope and just have a great time with it. So again, what I'm going to do here is I'm going to stop my share, and I'm going to go ahead and post the registration link for our webinar for the Jupiter conjunction. Now, I also want to let you know, too, is that for those that have been part of CFAS for many years, we are, you probably remember Mike McConville. And Mike McConville is joining me for one night on December 19th for a revisit of the Star of Bethlehem Planetarium program. So some of you are have been asking about that for many years. We are bringing that back this year only as a Zoom program. I'll also post that as well. But I hope to see you all on the 21st, and hopefully we have clear skies for those events.
Thanks, Derek. Yeah, this is pretty exciting. They're going to be pretty close. I was going to bring up it's a fifth the size of the moon, and then you said it too. I just fingers crossed, everybody, for clear skies that night. Okay, so next up on the agenda is me again. I'm going to spend just a minute on the moon, if I may. Just a minute on the moon. Real quick, so this month's object of interest on the moon is going to be Petavius. I think I'm saying that correct. It's French, and I took German, not French, so I hope I'm not mangling it too much. Where is it? It is at the southeastern limb of the moon along the edge of Mare Fecundatus, which I also don't think I'm saying correct. I would probably fail out of Hogwarts because of my Latin, but the English version of that is the Sea of Fertility. And so it's available very early in our monthly lunation, just past full moon. Wait a minute. Anyway, yeah, very early. So very early, and then after full moon, it starts showing up again. It's a pretty large crater on the side of the moon. Here it is in context along the side. This is actually a sunset shot. It's 184 kilometers wide, or 114 miles, depending on your preference there. And the central peak is about 5,600 feet above the crater floor, so it's about a mile high. It's very accessible, even with modest magnification, and it shows a lot of detail. Let's take a little closer look at it here. The big gouge that you see, get my mouse over here, the big gouge you see right here is Rima Petavius 1. And the outer wall is actually unusually wide for these types of craters. It has a double rim here. First time I imaged this, I thought, well, this is a stacking artifact, because what we do with lunar lucky imaging, we take all those video frames and try to align it and straighten it out. And I do have some, stacking and sharpening artifacts, but this double rim here is real. That's an actual feature of the crater. It's pretty cool. The best time to view it is either when the moon is very young, or right after full moon as sunset, which in this photo here is actually right after full moon as the sun is setting on this crater. Once the moon is overhead, a lot of the details start to disappear. There's actually 9 separate little peaks in this in the middle here. It looks like a lunar city. It inspires me to think of it as almost as a lunar city. If you had very poor optics and it was very blurry, when the light hits it just right, you could convince yourself that there was some sort of a moon colony here in the middle. Mr. Petavius himself, he was a French astronomer and theologian who published a celestial ephemerides for a number of years. So he was of the John Pinto and my streak, you like to do astronomy math and publish it in books. And so that is a minute on the moon. But we do need to talk about our lunar observing challenge. Last month's challenge was to observe the moon with binoculars and sketch it and see what you can see. Now, this image of the moon I took in my backyard. I had a scope set up, and then I went out in the front yard and got myself comfortable, and with a pair of binoculars, I made this sketch. Now, this is not anywhere near Bill Castro's quality of sketch, and I'm not actually being too lazy. I'm just not really very good at it. But to compare this, with the image, I think one of the important things about sketching at the eyepiece, and maybe in a few years I'll get much better at this, but when you're sketching, you're looking a lot more carefully. There are things that I saw in my sketch that when I was sketching, that I never really paid attention to. This is beautiful, and my eye is drawn to these contrasts in the photo, but a camera does not have nearly the dynamic range that the human eye does, nowhere close. And even if you had a camera with the dynamic range of a human eye, a computer monitor doesn't have the dynamic range of reality. So what you're looking at on the screen is very compressed compared to looking through a telescope or binoculars. And I've always said, and I'll say to my dying day, the moon is one of these objects that always looks better in an eyepiece than it does when you take a photograph of it. One of the things I noticed is right here, Tycho, you could see this lip sticking out into the dark. You could see this ring very, very prominent in binoculars, but in the photograph over here, it's sort of lost. You don't see it. It's not popping out at all. I also you don't see anything along here, but there was a very bright thing. You had a nice dark terminator, and out past the terminator, there was a very dark peak of the moon that was sticking up. And of course, I'm observing all of these different dark areas and then going back and labeling them. This is how you learn lunar geography, and it's how you learn to observe and look at things and notice the differences that you see visually. And I can't stress it enough, through the eyepiece, the moon, you can see much more than you can with the camera. So our next observing challenge for the moon is to observe, photograph, or sketch lunar rays in ejecta. Look at the moon while it's full. The full moon gets no respect. It gets ignored a lot, but there are actually features around some of these craters that only come out when the moon is full. I might call them werewolf lunar features, or they're much more prominent when the sunlight is overhead. So look at those, see if you can find some and sketch them and identify them, and I'll have more to say about lunar rays and ejecta next month when I spend a minute on the moon. And that is all. It's now Sharife Gazelle is going to talk to us about Artemis.
Right.
I may still be
Speaking
sharing.
of the moon.
Speaking of the moon.
Speaking of the moon, let me share my screen. And, oops. Let's try this again. Oops. There we go. All righty. So let me make this. All right, so we're going to be talking about space exploration, part of things. Talking about, oops, pause that. Returning back to the moon. So the Artemis program, you guys might be familiar with this, so I'm going to be giving you some updates as to what's going on with the Artemis program. And the timelines that I have in the presentation might be different depending on what's going on with different deadlines and whatnot. But we're going to be talking about why going back to the moon. Why are we doing that? The rockets that are going to be involved, and then also the missions that are planned as of now. So here is my finished Artemis drawing that I finished for this meeting just in time. As you guys know, Artemis is the twin sister of Apollo, who was the goddess of the moon. And let's see, in this drawing, I drew the stag, which was her companion, and the companion's name was Orion. So that would be a good reason why they probably named the program Orion. Why they named it Orion as the capsule for the Artemis program. So she personifies the path to the moon, which is why NASA chose that as the name of the program. So let's see. So why the moon? Why going back to the moon? First of all, it's a stepping stone to get to Mars. Specifically, the goal is to have a sustained presence on the moon. So to live and work on the moon would be the goal, and where would be at the South Pole. So the reason for that is that there's longer duration of sunlight on the South Pole, and it also has a direct line of sight with Earth, which makes things easier for communication purposes. So as far as landing sites, we've primarily landed more on like the middle and the part as of now, and the goal is to land on the South Pole because it's a lot flatter, there's a lot less craters, and there's also permanent dark spots, which are great for mining volatiles, which could be used for habitability reasons, sustainability on the moon. So why? This might be a question that comes up once we go back to doing that. And so one of the reasons is that we've only explored about 6% of the moon. As you can see in this picture, these are the US landing sites, all the Apollo missions, not counting the Chinese landings. But it would be like saying if we had lunch in London that we know all of Europe. And so we're familiar with all of Europe. So this is one reason, is to really go back and get a more in-depth look as to what's going on in the moon. For perspective, right now, the International Space Station, living and working last 20 years, 240 miles away in orbit. The next step would be the moon, which is 240,000 miles away, give or take. And then the following goal would be to go to Mars, which would be 54 million miles away. And so the moon, in this sense, would be a stepping stone to get us to Mars and to be able to do that. Temperatures, as you can see, are about 5,200 degrees. And so everything increases incrementally, which could prepare us on the moon to get to Mars. And how are we going to get there? So right now, the Space Launch System, the SLS rocket, which is being designed by headed off by NASA, and then a couple other companies that are responsible for designing and contracting out the core stage and the boosters. But the Space Launch System, the SLS rocket, you could see the two in the middle. There's a Block 1 and a Block 2 that are in the picture, and in comparison to the Space Shuttle and also the Saturn V. Once the Block 2 spacecraft will be built and launched, it'll actually have about 15% more thrust than the Saturn V, so it's going to be a much bigger and more powerful rocket. And the reason is that it's going to be able to have a lot more capacity for cargo and also for distance. So I'll let you guys read through the stats there if you want. But the top where the Orion capsule is will have a couple different payloads that can be switched out, so it can be adaptable for astronauts or for science and research. Currently on Artemis 1, which we'll get to in a second, it'll have 31 CubeSats on board, which will help to determine the science and the trajectory and all of the research that has to be done before we actually send astronauts back in space. So you can see how currently the Block 1 rockets are in production and kind of being developed, and then they'll evolve over time. So, the solid rocket boosters, the sides of the rockets, they're a lot of the same technology from the shuttle, from the space shuttles. They've just been evolved a little bit more to adapt to the needs for the Artemis program. The solid rocket boosters are currently at Kennedy Space Center, and they're just they're waiting to be assembled and to be attached to the core booster. And each booster has 7.2 million pounds of thrust, which is a lot. And they are contracted out by Orbital ATK. And yeah. In the center is the core stage. So the core stage is being developed by Rocketdyne. And it's a core stage that has never been flown before. So it has 4 RS-25 engines, and the propellant that's going to be used inside the core stage will be liquid hydrogen and liquid oxygen. And right now this is being tested in Michoud in New Orleans in that test facility. In order to do that, they have to go through a testing process called the Green Run. So this is pretty neat. If you go onto NASA's website and you type in either Green Run or just Artemis program, you can find videos of this firing. Very, very cool. It's basically a safety test where they're testing the core stage and the 4 RS-25 rockets to make sure that everything fires safely. So you can see the flame trenches in the picture over here and over here, and then the core stage in orange right here. And so they'll do a series of tests, and they've done, at the time that I was putting this presentation together, they had done 8, and I believe they had 1 more to do, and they had all been successful. So that's a great thing. So yeah, so this is the testing stand again for the core stage. And let's see, on the bottom you can see the barge that brought in, they didn't use a super guppy, I think, but they brought in the core stage on this barge over here. So it's currently at Stennis being tested. So yeah, and then cryogenics, that was the next test, that the cryogenics were going to be loaded and fired at the time that this was being done. So on to the missions. First mission for Artemis program will be Artemis 1. It will be uncrewed, and the Orion capsule will be tested out. The goal is basically to see if this thing can fly, get it to the moon, and testing different life support systems on board, checking telemetry, the flybys of the moon, obviously important heat shields of the test of the space capsule, and then other crewed missions. So, okay, so they will be launched from Kennedy Space Center, and then the first Artemis 1 mission will launch from Kennedy Space Center, travel into low Earth orbit, get into perigee orbit, and then enter translunar injection into the moon, be captured by the moon, do its tests, launch its CubeSats, test its science, and then come back to Earth with retrograde orbit. So I can post this picture, or you guys can look it up also on NASA's website, because this is very small text. Let's see, looking at all these comments for a second, but I'll go back. All right, and I'll go back and read through the chat after. So on board will be 2 the anthropomorphic test dummies that will be on board, and they're going to be wearing the AstroRad vest, which I actually saw launched onto a CRS mission from Wallops last year. They did kind of a preliminary test for the AstroRad vest, and it's a radiation vest that's going to be launched. And so this one specifically is meant for female astronauts, and they have radiation protection in appropriate areas. So these are the 2, they have Helga and Zohar, which are the test devices that are going to be launched in there in Artemis 1. So that'll be neat. And the vests are really neat. They're made kind of like this thick, really thick foam that you would never imagine. It's just really thick and weird honeycomb shaped foam, but yeah. So then Artemis 2 planned 2023. Again, the dates might be changing, probably will. This one will be crewed, and the astronauts that are on this mission will travel further than any other humans. So they'll go past the moon and then come back to Earth. So they will not land on the moon in Artemis 2. And they'll go 40,000 miles, like I said, beyond the moon to test all the life support and everything. Then Artemis 3 dates will be crewed, and they will be landing on the south pole of the moon. And the goal for the Artemis program is to land once a year onward. So every year there'll be a landing, and the astronauts will be planned to live there for about a week every time, and then they'll come back. So there will be habitability modules that will have to be built in order for that to actually happen, where they can live and work for 1 week at a time. And there will be multiple Artemis and SLS rockets ready to go for launch for this to happen. In order for that to happen, there have to be human landing systems. And so these habitability modules, these landing systems are currently up for contract, and they're figuring out who's gonna get the contract, maybe more than one, not sure. But Blue Origin, SpaceX, and Dynetics are all up for competition for developing the landing systems where the astronauts will live during this time. So the main goal of the Artemis project, of the Artemis program, is to learn to live and work on the moon to become an interplanetary species. So like I said, moon is the stepping stone to then go on to Mars and onward. So that is the end. Let me stop sharing, and if you guys have any other questions. Let's see. Yeah, the temperature on the moon, let's see. Yeah, the variability, that was just the extremes of the temperature. So you're right, Richard. All right, the longest we've been on the moon, I'm not sure what the longest mission was. Does anyone know what that is? I can look it up if not.
It was only a few days.
Yeah, it wasn't a week or anything, because it was just like, yeah, was it Apollo 17? I can look it up later on. It'll put it in the chat. But yeah.
Yeah, they were surprisingly short. It's like, if I want to go all that way, I want to stay a while, you know?
Yeah. So the SRBs on SLS reusable like the shuttle. That's the plan, is to use as much of it, reuse as much of it as possible for sustainability. So yeah. Any other questions? Yeah.
That was a great talk. I love your art, but I'm glad it wasn't just about the art. So that's pretty cool.
I tried to get it in. You tried to finish it in time.
Yeah.
Awesome. All right. Well, I'm going to mute myself.
All right. Thank you. So just in case my internet went out for some reason, I switched over to my my hotspot on my phone during the last talk, not before Sharife. So if I don't finish up, Derek or somebody may have to jump in. But next we have Taryn, who's going to give us a book review. And I solicited last month and will continue. If you've read a great astronomy book, history or math or otherwise, you are welcome to come on. And we very much would like you to share your experience with everybody else. So I'm going to turn myself off.
Hello, everybody. In keeping with the history of astronomy adventure that we've been kind of following through, this book kind of pertains to that. The first session, we kind of looked at the Ptolemaic theory of what was popular in the Middle Ages and Renaissance as far as how people viewed the stars, and then we kind of went forward and looked at astrolabes, one of the major tools that they used. Well, if you're not interested specifically in how to recreate what the ancients did, you might be interested in how we got to where we are. And this book, if my slideshow will ever start, let's see here, is a good introduction to that. It's the history of astronomy. Well, the book is called Cosmos, an illustrated history of astronomy and cosmology, revised edition by John North. John North is a major figure in the history of astronomy. He lived from May 19th, 1934 to October 31st in 2008, so we've lost him recently. He did mathematics at Merton College in Oxford, where he met his wife, and then he also read for philosophy, politics, and economics. He went on later to do an external degree at the London University in astronomy, physics, and applied math. He was a professor at a university in London, and he was a member of the Royal Netherlands Academy of Arts and Sciences, and briefly a member of the Astronomical Association. He was the author of over 17 books. This book could very well be considered his magnum opus. It's kind of the last one he wrote. It is a history book in the very strong sense of the word. So we talked before about the history and practice of ancient astronomy by Evans. That book was very much how the ancients did astronomy. This is very much a history of astronomy. And it reads like a history. The author is British and is kind of maybe perhaps wordy for some readers, but I think if you're interested in the topic, his writing style is as such that it will keep you going. The book is very, very thick. I don't know if you can see it here, but we're at, well, 856 pages or some amount. It covers the topics very, very in-depthly, starting with the Neolithic period and going all the way until about 2006 when the revised edition was published. The book also is remarkable for its diversity of topics. Generally, like most of Western astronomy, has went from the perspective that everything started in Egypt, maybe the ancient Greeks picked things up, and then it was distilled within the medieval Islamic world and brought back to Europe during the Crusades, and just kind of developed in Europe until what we have today. This book has a lot of information about what happened in China and Japan and some of the Asian countries. It divides the Islamic part into two parts, the Middle Eastern Islamic part and then like the Western Islamic part, like North Africa and Spain, as well as it has 10 pages on North American astronomical traditions, which is rare to see in a survey work of this kind. As well as there's a good amount of Indian, like the country India, their astronomical traditions as well. Now, some authors have compared this to the more famous Cosmos by Carl Sagan, and saying that it was just basically a rehash of that work. But they kind of have different goals. Carl Sagan was trying to get people fascinated in science and astronomy, and this author is just really trying to walk through the high points of astronomy from the beginnings of man looking at the stars and until the time he published the book. It's got a fairly nice introduction to the radio astronomy and talks all the way through with some of Hawkins' work and some of the more recent stuff as well. The math level for this book is only, I think, high school geometry. I think if you have a good grasp of high school geometry, you should be fine with this book. And some people find history reading very, very dry. Again, I think if you have a love of the topic, this book should be fine as far as that goes. I wanted to share the table of contents here because I think that is one of the things that I always look for when I'm evaluating a book to see if it's something I'd like or not. 20 chapters, starting with prehistory, ancient Egypt. The chapter on Mesopotamia is actually very good. It's got one of the better introductions to Mesopotamian planetary theory that I've seen around. It covers the Greek and the Roman worlds just in a very introductory way. The pre-Columbian astronomy is the North American section. Indian and Persian astronomy, of course, we mentioned. And then where I think we best off is it goes into the Copernican period, New Empiricism period, the rise of physical astronomy, which was mentioned in Dr. Shane's talk, where we started seeing that physics and astronomy was put together and going all the way into some like putting astronomical observations in space. And the author is very intent that this is not a book that historians would probably be appreciative in because it's a generalist book. So it's like a great history book for anyone who has an interest in astronomy, not a astronomical book for historians who have an interest in astronomy. He said that kind of book probably wouldn't be worth reading anyway. And he did note that he did leave several indigenous traditions out, but the book is so thick already, and he was trying to cover the major thread of the things that contributed to the astronomy that we have today. But this book is still remarkable in its breadth and its depth, and you probably couldn't find a better generic survey of history than John North's Cosmos. It's a shame that we lost him because we won't be getting any more updates for it, but it takes us to 2006, which is a good place to that we can, for the most part, keep up past that time. Let me stop my share, see if we have any questions in the chat. No. Is there any questions about the book for the Cosmos?
What does it cost?
I think when I checked earlier today, it was around, I think it was around $50. Let me just double check that price real quick. It's not something that could be finished in a semester in a college classroom. Yeah, the paperback right now is $52. You can get a used copy on Amazon for $29.39, and there is no Kindle copy. But it's a great book for anyone who wants to have a general survey to get breadth. Of course, if you want to specialize in any particular point, you do better getting a specialty.
Does he include further reading so that if you do want to dive into any particular one?
He has a great bibliography in the back. That's one of the things I meant to mention that I forgot to mention. And he kind of goes by chapter in a paragraph style and telling you why he's chosen the specific readings for each chapter. And so it is a good book in that range as well. Written at a scholarly level for non-scholars, more interested people again. But
Cool. Thanks very much. I might have to add that to my list as well. Somebody made a joke once. You can tell what kind of person somebody is by the kinds of books they keep on their shelf but haven't read, because most of us have an appetite for these books that outpaces our ability to or time to read them all. Or maybe that's just me. I don't know.
Richard, nobody told you that's what the afterlife is for.
Oh, excellent. Excellent. It's I feel like a lot of people have been going nuts with the pandemic, with the lockdown, but I work at home, and I think I could actually survive a trip to Mars. If you put me in a little box and gave me enough books, I would probably be just fine for 6 months or so. Can't say, yeah. Anyway, I think that wraps us up for tonight. Have I forgotten anything? Any of the committee chairs, or anybody else on the board? If I forgot something, it's sort of a speak now or hold your peace. Don't forget.
Anybody mention Arecibo? About an
no,
update?
we did not. We did not. If you haven't heard, Arecibo suffered a fatal collapse. And the video is quite visceral. I saw the drone footage, and then I saw some footage on the ground with the sound and everything. It was kind of terrifying, actually, if you had been anyone near. But it's destroyed beyond repair. Well, I guess you could bulldoze it and start over, but it's in pretty bad shape.
Yeah, and the last news was that actually UCF was part of the caretaker.
Yes.
Caretakers for it. So
yes, I have a friend who's associated over there, and said a lot of people are out of work.
Right.
That's cold. Can you imagine some of these projects we're talking about? The gravity wave, it's going to launch in 2030. Can you imagine spending 30 years on a radio astronomy project, and you finally got time, and then the whole instrument's destroyed? And I mean, it's just it's really heartbreaking for the people involved there. But so just a reminder, next month we are going to do a pre-show. So you got a telescope, now what? So tell your friends and family. I imagine I am not the only one in the club who has had people coming out of the woodwork. What kind of telescope should I buy for Christmas? I've been sending them to our YouTube link from the workshop that we did a few months ago, and we'll do sort of a post one. Well, this is what you got. How can you make the best of it? Also, our speaker next month, Tricia, you mind if I if I steal your thunder on this? Are you here? Do you want to tell people?
No, it's actually Frank's thunder.
Maybe it's Frank. Yeah, Frank did it. Frank, you want to tell everybody who you nabbed for next month's meeting?
Yeah, next month we have astronomer Phil and how the universe works, and the Bad Astronomy blog on sci-fi.com. Yeah, we managed to get him for our main speaker next month, and he's going to be talking about exoplanets in a talk called Strange New Worlds.
Strange New Worlds. Yes, Phil's he's well-known speaker and columnist, and I heard he was a bad astronomer. He had a TV show for a short period on Discovery too, called Bad Astronomy.
That's right. That's right.
Yep. So okay, so that wraps it up then for tonight, I guess. And I want to thank everybody for giving us a couple of hours on a Wednesday night. Don't forget, it's freaking beautiful outside. You need to get outside and at least look at the night sky. Look up at Orion. It's gorgeous right now. It's been so cloudy for so long. I know Frank's got a system up and going. I got a system 2/3 of the way up and going in the backyard. And as soon as I log off, that's where I'm headed to get things the rest of the way going. So get out there and do some astronomy. And don't forget to share your work, your notes, sketches, or photographs with us for the next meeting. And I hope to, oh yeah, well, there's stuff going on too. Don't forget the webinar about Jupiter and Saturn. coming up. That's going to be really cool. I think a lot of people are planning to do photographs of that and observe it. It's really too bad we can't have a big outreach event with a whole bunch of people. Really poor planning on whoever planned this conjunction at this point in time. We'll have to have some words with them. So everybody stay safe and keep looking up, and hope to see you all safe and sound again in January. Oh, Happy New Year. Yeah, it'll be New Year too before we all see each other again. So take care. Signing off. 3, 2, 1. Derek's the one who's going to pull the plug, actually. All right.
Sony and set up in a heartbeat.
Goodbye.
Later.
Yeah, thanks. Yeah, Eric.